So let me start. Uh, Today I'm going to talk about this section 2.7.2 diagonalization and polar decomposition. Okay, using the three eigenvectors as the three columns, we can construct the modal matrix. What is modal? Modal. Modal. Uh, okay, modal matrix. Modal matrix of the given matrix A. Let us denote the modal matrix by M. Then M equal x1, x2, x3. Then it is clear that M transpose A M equal lambda 1, lambda 2, lambda 3. This procedure, how do you know this? This procedure amounts to choosing new Cartesian systems aligned with the principal directions of the quadratic. Principal direction of the quadratic. The principal direction of the quadratic. Quadratic. Second order. That is, we choose the principal coordinate system x prime using x prime I equal mij xj, or x prime is m transpose x. Multiplying equation 2, 1, 2, 3 by m from the left and by m transpose from the right, we can express matrix A as this is called the spectral X representation of A. How is matrix A? Hmm. So far, we have been concerned with a symmetrical matrix A. The polar decomposition applies to any square matrix B. Polar decomposition refers to factoring B in the form B equal RU or B equal VR, where U and V are symmetric matrix and R is an orthogonal matrix, rotation matrix. Using RR transpose equal 1, we get U square is B transpose B and V square B transpose. To find U and V, we need the square root of the matrix on the right-hand side of the preceding equation. After U and V is found, R can be expressed as R equal B U inverse equal V inverse B. This brings us to finding the square root of a symmetric matrix, say C, or in general any function f. C of a matrix. We begin by assuming the function f, C, has a converging infinite series expansion in C. What is the complication? In the form we need the square root of matrix on the right-hand side of the preceding equation. So then This brings us to finding the square root of a symmetric matrix, say C, or in general any function f of C of a matrix. We begin by assuming the function f of C has a converging infinite series expansion in C. Okay. The functions we have in mind are C of 1/2, C to the power of 1/2, sine C, exponential C, etc. The corresponding functions of a single variable, say x, are x to the power 1/2, sine x, exponential x, etc. The generic matrix function f has the corresponding function of a single variable f. Our symmetric matrix C has three orthogonal eigenvectors xi with the corresponding eigenvalues lambda I, multiplying equation 2, 1 to 9 from the right by xi, we see that f lambda I is the eigenvalue of f corresponding to the eigenvector xi. The eigenvalues of c to the power 1/2 sine c and exponential c are lambda I 1/2 sine lambda I and exponential I respectively. Next, we use the Cayley-Hamilton theorem to reduce equation 1 to 9 to a quadratic in C, provided we are still dealing with 3 by 3 matrices. Then the eigenvalues satisfy f lambda I C0 plus C1 lambda I C2 lambda I square I equal 1 to 3. For example, to find the square root of C, we use lambda I to the power 1/2 equals C0 plus C1 lambda I plus C2 lambda I square. And solve for Ci. We substitute these coefficients in equation 2, 130 to get c to the power 1/2. We may anticipate complications when the eigenvalues are not distinct. If lambda 2 equals lambda 1, we follow the Frobenius limiting process. We begin by assuming lambda 2 equals lambda 1 plus epsilon, then one of the three equations for Ci becomes f lambda 1 plus epsilon equal. We subtract the equation corresponding to lambda 1 and divide by epsilon we have. As epsilon go to 0, we obtain the needed additional equation. All of our discussion in the last two subsections are limited to 3 by 3 matrices. Extension of the preceding result for square matrices of any order is straightforward. Let's see the example. Example, polar decomposition. Suppose we want to factor the matrix like this. The factors U, V, and R are obtained from U square equals C equal B to B transpose B, blah blah blah. R is BU inverse V equal BR transpose. The eigenvalues of C are 9, 16, 36. Using the expansion like this, we have simultaneous equations. The solution of this system are something like this. Writing C to the power 1/2 is something like this. So we get U is like this, R is like this, B equal like this. Okay, so let's stop it here. So we kind of finished chapter 2.